Hello everyone, today will be our last lecture on research and empirical methods in computer science. For today, we are going to talk on a topic called ANOVA. Before we start, let's recap back what we have go through on week 13, yeah? So we already covered on the statistical estimation and parameter estimation, central tendency, and also the confidence interval. Right? So do remember what are those the parameter estimation. So they are includes the point and also interval estimate. Right? So what is the statistical estimation? It's the process of making inferences about the whole population based on information obtained from a sample from that population, right? So an estimate of a population parameter may be estimated in two ways. They are point and also interval estimate, right? For the point estimate is defined as a population parameter in a single value of a statistics. For example, the sample mean mu is a point estimate of the population mean. Alright, so for the interval estimate is defined by the two numbers between which a population parameter is said to lie. How about the confidence interval? So confidence interval is a sample statistics with a plus minus of the some margin of error. Right, this is all about the week 13. So for today, we are going to cover two topics under ANOVA, which is the ANOVA and also the evaluation of the research. Now, we start with a question. What is exactly the ANOVA? What is the ANOVA itself? Right? So, for the people that who don't have any background on the statistics, let me consider one scenario, okay, for me to explain the ANOVA. Right? So consider a scenario where we have three medical treatments to apply on patient with similar disease. Right? Medical treatment to apply on patient with similar disease. Right? So when we have the test result, one approach is to assume that the treatment which took the least time to cure the patient is the best among them. What if some of these patients had already been partially cured, or if any other medication was already working on them? In order to make a confident and reliable decision, we will need evidence to support our approach. So this is where the concept of ANOVA comes into play. A common approach to figure out a reliable treatment method would be to analyze the days it took the patients to be cured. We can use a statistical technique which can compare these three treatment samples and depict how different these samples are from one another. Such technique which compare the sample on the basis of their means, compare the sample on the basis of their mean is called ANOVA. ANOVA, or analysis of variance, is a statistical technique that is used to check if the means of two or more groups are significantly different from each other. Another checks the impact of one or more factors by comparing the means of different samples. We can use ANOVA to prove or disapprove if all the medication treatments were equally effective or not. Another measure to compare the sample is called t-test. When we have only two samples, t-test and ANOVA give the same results. However, using a t-test would not be reliable in cases where there are more than two samples. If we conduct multiple t-tests, for comparing more than two samples here, it will have a compounded effect on the error rate of the result, right? So meaning that if you have more than two samples, all the statistical analysts will use the ANOVA, right? If you have two samples, then it's advisable to use the t-test. Okay. So now let's go one by one on the terminologies related to ANOVA. The first one is the grand mean, right? Grand mean, right? So mean here is a symbol of arithmetic average of a range values. Average value, right? There are two kinds of means that we use in ANOVA calculation, which are separate sample means and the grand mean. All right? Separate sample mean, mu1, mu2, and mu3, and also the grand mean, which is mean, right? So the grand mean here is the mean of sample means of or the mean of all observation combined irrespective of the sample. Now let's go to the second terminology, hypothesis, right? We have two. We already covered this one in the previous lecture, null and also the alternative. Now let's look into the hypothesis terminology in terms of ANOVA, right? Considering again here our above medication example, we assume that there are two possible cases. Either the medication will have an effect on the patient or it won't, totally won't. So these statements are called hypotheses. A hypothesis is an educated guess about something in the world around us. It should be testable either by experiment or observation. Just like any kind of hypothesis that you might have studied in statistics, ANOVA also uses a null hypothesis and an alternate hypothesis. The null hypothesis in ANOVA is valid when all the sample means are equal. Okay, when all of the sample means are equal, right? Or they don't have any significant differences, right? Thus, they can be considered as a part of a larger set of the whole population. On the other hand, the alternate hypothesis is valid when at least one of the sample means is different from the rest of the sample means. In mathematical form, they can be represented as where mu1 and until mu L, right, belong to any two sample mean out of all the sample considered for the test. Alright. So in other words, the null hypothesis states that all the sample means are equal, or the factor did not have any significant effect on the result. Null hypothesis meaning that mu1 equal to mu2 or ... until equal to mu L. Right? So whereas the alternate hypothesis here states that at least one of the sample means is different from another, but we still can't tell which one specifically, either it mu1 or mu2 or mu3 or mu L. Right? For that, we will use other method that we will discuss later in this lecture. Another terminology is the between group variability. Right? Consider the distribution of the two samples in the figure 1. Right? In the figure 1. Here, the figure 1. Okay. So, okay, here is the figure 1. Okay, this is the figure 1, right? See the pointer, right? So, consider distribution of the two samples in figure 1. As these sample overlap, you can see it's overlap, the individual means won't differ by a great margin. Hence, the difference between their individual means and grand mean won't be significant enough, right? Now consider figure number 2. These two sample distribution in figure number 2. Alright, so what is the difference between figure 1 and figure 2? So as the sample, okay, figure 2, the sample is not overlap. Right, so as the samples differ from each other by a big margin, the individual means would also differ. The difference between the individual means and grand mean would therefore also be significant. Such variability between the distribution called between group variability. It refers to variation between the distribution of individual groups or level as the values within each groups are different. Each sample is looked at and the difference between its mean and grand mean is calculated to calculate the variability. If the distribution overlap or are close, the grand mean will be similar, like shows here. Little discrimination. Right? To the individual means whether if the distribution are far apart, right? Differences between means and grand mean would be larger. Okay, see this one, the figure number 3. Right. Now another terminology is no. This is how I'm going to show you how we're going to calculate the between group variability. Right? We will calculate between group variability just as we calculate the standard deviation. Yeah. Given the sample means and the grand means, we calculate it as shown in the figure 1. Alright. We also want to weight each square deviation by the size of the sample. In other words, a deviation is given greater weight if it's from a larger sample. Right? So hence, we'll multiply each square deviation by each sample size and add them up. This is called the sum of square between group variability. Right? SS between. Here. Formula number 1. Sum of squares for between group variability. Right? So there is one more thing we have to do to derive a good measure of between group variability. Again, recall how we calculate the sample standard deviation. Alright, so we find the sum of each square deviation and divide it by the degrees of freedom. For our between group variability, we will find each square deviation, weight them by their sample size, sum them up, and divide it by the degree of the freedom, df between, which in the case of between group variability is the number of sample means k minus 1. Alright, so this is the formula number 2, how we want to measure between group variability. Alright, so what is the within group variability? Right, so within group variability, right, consider the given distribution of 3 samples, 1, 2, 3, in figure number 1. Is overlap distribution of 3 samples. As they spread, variability of each sample is increased. Right? So, their distribution overlap and they become part of the big population. So, C is overlap. Now, consider another distribution. Figure number 2. Another distribution of the same sample or the same 3 sample but with less variability as shown in figure number 2. Okay? Non-overlap. Alright? Although the means of sample are similar to the sample in the above image, they seem to belong to different populations. Such variation within a sample are denoted by within group variation. It refers to variation caused by differences within individual groups or level, as not all the values within each group are the same. Each sample is looked at on its own, and variability between the individual points in the sample is calculated. In other words, no interactions between samples are considered. So how do we calculate within group variability? How do we calculate within group variability? Okay, we can measure within group variability by looking at how each value in each sample differ from its respective sample. So first, we'll take the square deviations of each value from its respective sample mean and add them up. This is the sum of squares for within group variability. Right? So, like between group variability, we then divide the sum of square deviation by the degrees of freedoms, PF within. Yeah, PF within. Right? To find a less biased estimator for the average square deviation. The average size square from the shows in the figure 1. But for within group variability, MS within, this time the degrees of freedom is the sum of the sample means n minus the number of samples k. Another way to look at degrees of freedom is that we have the total number of values and subtract 1 for each sample as shown in the formula 3. Mean square for within group variability, MS within. Another terminology in ANOVA is the F statistics. Okay, the statistics here which measure if the means of different samples are significantly different or not is called the F ratio. Lower value of the F ratio means that more similar are the sample means. In that case, we cannot reject the null hypothesis. Remember what is the null hypothesis in the ANOVA? When all the mean of the samples are equal. Alright? So, F between group variability or within group variability. Okay? So, F between group variability or within group variability. So, it's pretty intuitive. Alright? So, F equal to between group variability or within group variability. Okay, so that formula is pretty intuitive. The numerator term in the F statistic calculation defines the between group variability. As we read earlier, as between group variability increases, sample means grow further apart from each other. In other words, the sample means the samples are more probable to be belonging to totally different populations. This F statistic calculated here is compared with the F critical. With the F critical value for making a conclusion. In terms of medication example that we discussed just now, if the value of the calculated F statistic is more than the F critical value for a specific alpha or significant level, okay, normally we set at alpha is 0.05, okay, so then we reject the null hypothesis and can say that the treatment had a significant effect. So in the graph, this is where the F critical value situated. Alright, so unlike the Z and T test distribution, the F distribution does not have any negative values. Why? Because between and within group variability are always positive due to squaring each deviation. Therefore, there is only one critical region in the right tail, right? Here, showing the blue shaded. If the F statistic lands in the critical region, we can conclude that the means are significantly different and we reject the null hypothesis. Again, we have to find the critical value here first to determine the cutoff for the critical region. Normally, we use the F level for this purpose. Right? We need to look at different F value for each alpha or significant level because the F critical value is a function of two things, which is the F within and the F between.